So our next speaker is Ki-Hao Guo from Purdue University. So feel free to start.
Yeah, thank you for introduction. Yeah. Okay. Hello everyone, thank you for being here. I'm Ki-Hao Guo, a graduate student from X Math Group at Purdue University. Today I will introduce our recent progress about using driven-dissipative dynamic in superconducting system to create artificial quantum reservoirs, and I will also show its potential application. So why we need an open quantum simulator? In physical world, matter always interacts with its surrounding environment, involving the exchange of particles and energy. So to simulate this, we need some open quantum system coupled to engineered buses. So it would allow us to simulate transport experiments in real quantum material, and it can help us to prepare and probe some many-body quantum states. We can also use an open system quantum simulator to explore some open questions in fundamental physics. For example, it may deepen our understanding of quantum thermodynamics. Okay, an open quantum simulator contains two main components: the coherent dynamic and the controllable dissipation. For a concrete example, here I show a bus-coupled lattice system. For the coherent part, we have short and long-range hopping, on-site and many-body interaction, disorder, and we may also have a coherent drive. Now let's shift our focus to the incoherent part. We can add some external buses like drain, source, additional defacing, and measurement. These buses may lead our system to some steady states or out of equilibrium state, which can greatly enrich the phase of matter in this system. Okay, now I will show you how we build a bus-coupled lattice in superconducting system. The first step, let's take a closer look to how we build a highly coherent lattice. The illustration you see here is the design of our chip. Here we have 4 tunable transmon qubits. They are capacitively coupled to the nearest neighbor sites. The qubit array naturally formed the 1D Boson-Hubbard lattice. In the 1D Boson-Hubbard lattice, the hopping rate of photon between two sites is about 6 MHz. And we also have on-set microwave photon interaction that is about 250 MHz. The typical coherent time of our device are larger than the time that photon hopping in our lattice. Therefore, superconducting system provides a promising playground to build a highly coherent lattice. Now take the same device. So we want to build a quantum buses from the driven-dissipative dynamic. So where is the dissipation from? The answer is the readout resonator. This illustration shows the interaction between the qubit and the resonator. They can be described by a large-detailed James-Cumming model, and actually there is no direct transition between the qubit and resonator. So what we can do is that we can modulate the qubit frequency and try to produce the parametric coupling between the qubit and the resonator. We have two kinds of interaction: red sideband and blue sideband, which corresponds to swap the population of different subspace in this combined system. With the faster decay of the photon in the resonator, we can effectively build the drain and source bus, which corresponds to incoherently remove or fill a particle into one qubit. We can see the reduced qubit dynamic. For the right sideband, we can find that the qubit population will decay to 0 eventually. And for the blue sideband, it will go to 1. I will use the drain and source buses to refer to the incoherent process in the rest of this talk. Now let's summarize what we have now. Yeah, beyond the coherent lattice, we still have highly tunable buses. The tunability of our buses contains the effective string and the detuning of our bus. And we also have the location and time freedom. That means we can select where and when we couple the buses to our coherent lattice. Okay, now we can discuss how to utilize this single-site buses, drain and source buses, to a many-body quantum system. Firstly, let's consider a simplified scenario, a two-site model. In this energy diagram, the eigenstate of a single particle manifold are the superposition state plus and minus. Now we can couple a single source bus to one qubit and pump the lattice to the minus state. The red plot shows the population of different eigenstates. We can observe that in the first stage, the population of the minus state increased a lot to about 90%. However, despite our efforts to maintain the lattice to the minus state, the defacing will cause a leakage from the minus subspace to the plus, and then the plus will also be influenced by our source bus. And then, after a long time, we can expect that nearly all the population will be pumped into 1-1 state. To address this challenge, our solution is to couple another dream bus to the other qubit. This can help us to remove particle from the unwanted subspace back into 0, state and redirect it back to the minus state. This protocol can be regarded as a kind of autonomous error correction of defacing error, and we can keep the target state as a dark state. With the two-bus strategy, we can stabilize the matter state with a fidelity about 95%. So now we can consider how to extend our method to a larger quantum system and try to understand what will happen in a real many-body quantum system. Here we consider a four-site Boser-Haber lattice, which form the lattice band structure. In different particle number manifold, we have discrete energy level. So now we can add a single source bus to one qubit and pump the lattice to the ground state of one particle manifold. However, just like what happened in the two-site case, the defacing will cause leakage from the ground state to other eigenstate, and then this state will be pumped to other manifold. So now we can introducing another dream bus to solve this problem. It can help us to remove particle from this subspace. We can see the red plot. The red plot shows the population of different eigenstates. Use this protocol when the population of one particle manifold ground state saturated. We can change the frequency of right sideband and blue sideband to the transition of two particle manifold and the other manifold. The mean population will be pumped into the ground state of each manifold, will be pumped to each manifold sequentially. So now we can prepare many-body eigenstate with different particle number, which enable us to study the behavior of many-body eigenstates. Beyond the preparation of many-body eigenstate, we can even engineer effective chemical potential for photon system. That is very hard. So with a combination of a broadband, source bus, and dream bus, we can stabilize a many-body quantum state with a specific energy and particle number. In theory, this kind of state a kind of generalized Gibbs state with zero temperature and finite chemical potential. So let's conclude by how we build a broadband source bus. So now we can build a broadband source bus by the time sweep of a narrow sideband bus. This plot shows our pulse. Yeah, the red line shows the amplitude of our pulse, and the blue line shows the frequency of the bus varies with time, crossing different transition frequency in this system. Our numeric, so this kind of protocol can be regarded as a kind of continuous analog to the sequential preparation. Our numerical simulation results shows that this protocol outperforms the sequential preparation, enable us to prepare the multiphase with even higher fidelity. We also have a preliminary data for this. If you are interested about this, we can discuss more. Okay, now I will give a quick outlook. So now we can engineer local bus, local gain and source bus. And actually, we can also build some non-local bus, which can help us to, So we can couple 2 qubits to 1 resonator or waveguide to build this kind of non-local bus, which can help us to produce a long-range entanglement in circuit QED system. We can also stabilize some effectively thermal state and use this thermal state to prepare many-body thermal state, which can help us to build some thermal engines or perform a finite temperature transport experiment. Our ultimate goal is to build some universal open quantum simulator with spatially, spectrally, temporally controllable buses, and use this to control and probe many-body quantum state with colorful properties. That's all. Thank you.